Louisiana using a tree-based algorithm. So please go ahead when you're ready.
Okay, so now I will discuss another paper, and actually it was one of the papers that we used in the software that I just discussed. So this paper is related to the prediction of the field performance of asphalt concrete overlays in Louisiana. So structural overlays are the most common rehabilitation treatment used in Louisiana. So the 1993 AASHTO design procedure is used to determine the required overlay thickness, and the design pavement service life is one of the key inputs that is used in this design procedure, and it's typically assumed 20 years. However, the actual pavement service life in Louisiana is rarely monitored. So this suggests that the overlay thickness designed with this procedure using pavement service life of 20 years, it may not last the entire design period without additional maintenance or rehabilitation activities. So this takes us to our objectives, which is to evaluate the field performance of asphalt overlays in Louisiana. So in specific, we evaluated the immediate benefits of overlays as well as the long-term field performance. We also developed an extreme gradient boosting, which is a machine learning algorithm. So we developed a classification model to predict the long-term benefits of structural overlays based on the field conditions. So this flow chart shows the methodology. So first we collected our data, and after that we evaluated the long-term benefits and the immediate benefits. So we evaluated the immediate benefits in terms of the index jump, and the long-term benefits were evaluated in terms of the pavement service life, in terms of all the distresses. And based on this pavement service life, or let's say the minimum value of this value was considered as a critical pavement service life, which we call PSL star. After that, we analyze the pavement service, we analyze the PSL star against the input variables, and we could develop a machine learning model that could predict the PSL star based on the project conditions. After that, comparing PSL star with the assumed value of 20 years, we could adjust the asphalt overlay thickness. So this slide, it shows how we identified the candidate asphalt overlay project, and it's the same like the slide I showed in the previous presentation. And this background also shows discuss the indices that we included in this study. So we included the random cracking index, the roughness index, the rotting index, and the PCI, which is overall pavement condition index. And again, all of these indices, they range from 0 to 100, with 100 being perfect. So let's say that we have a roughness index of 100. This means that the road has, there is no any roughness problems with this road. So in our study, 141 projects were collected and analyzed. And for every project, we collected the following variables: the total length of the project, and these are the minimum and maximum values for the 141 projects. So for all the projects, we collected the length, the construction dates, the treatment dates, the pavement age, the overlay thickness, the traffic volume, the pre-treatment conditions in terms of the PCI, RCI, roughness index, and the rotting index. So this is the collected data. And based on the collected data, we first started with evaluating the short-term benefits. So we evaluated the short-term benefits through calculating the index jump. So we did this for every project and for every index. And it's simply the first index after the overlay application minus the pre-treatment index. So this figure shows the performance jump for the pavement condition index, and once we calculate the index jump, we plotted the values against the pre-treatment index. So as expected, almost all the projects had a positive performance jump for all the indices. And this, again, this was expected, and this indicated that the asphalt overlay corrected all the pavement deficiencies. So that's why in the following analysis, when we were evaluating the long-term field performance of asphalt overlays, we considered all of these indices. So after that, we evaluated the long-term benefits of the asphalt overlays in terms of the pavement service life. And this figure shows how the pavement service life is calculated. So this is a performance curve. So first, this is the pre-treatment field data, which is the PCI or whatever index we are using before applying the overlay. And after we applied the overlay, the index jumped up to 100. And then this is a performance curve for the overlay. So this is the field data that we have. And then using this field data, we developed a simple regression model to be able to predict this data. And then using all of these points, we predicted the time for the PCI to drop to a threshold value of 60, and this is the pavement service life. So again, we calculated the pavement service life for every index, PCI, rutting index, roughness index, and RCI, and for every project of the 141 projects that we had. So for all the projects, the average pavement service life was about 22 years for the PCI, 20 years for the RCI, 29 years for the roughness, and 20 years for the rutting. And after that, we determined the PSL star that is a minimum for every project. It's a minimum of all of this pavement service life. So we found that the random cracking and the rutting were the limiting distresses for 49 and 30% of the projects, which means that in Louisiana, the most common distresses are the random cracking or the cracking in general and the rutting. So after that, we wanted to see the correlation or the impact of the pre-treatment condition on the pavement service life. So we plotted the average pavement service life, and again for the different indices, again as the pre-treatment pavement conditions. And as we can see that longer pavement service life is achieved with better pre-treatment pavement conditions, and this is a general trend, and again, this is for all the indices, that as the pre-treatment pavement condition is higher, you achieve a higher pavement service life. And that's why when we developed our machine learning model, we included the pre-treatment pavement conditions. So generally here we are trying to see whether the pre-treatment conditions significantly impact the pavement service life. And we did the same for the to see the effect of the traffic as well as the overlay thickness. So this one shows the effect of the traffic on the pavement service life, and we found that projects with the lower traffic had lower pavement service life. And we found also that higher pavement service life was achieved as the overlay thickness increased. So this is a critical pavement service life that I discussed before. So it's simply the minimum value. It's the minimum value of all the pavement service life that we calculated. And we calculated PSL star to ensure that the pavement will not fail due to any distress along its service life. So as you can see in this figure, this is the PSL stars that we calculated in our study. And this is the 20, which is assumed value. So we can see from this figure that about 75 of the projects had PSL star less than 20 years. And this suggests that the design overlay thickness using the AASHTO 1993 may not last the entire design period without the need for additional maintenance or rehabilitation activities. So that's why we developed a model, a machine learning model. So we developed an XGBoost model, and again, XGBoost, it's a tree based in simple algorithm. And in this model, we used 7 variables to predict the PSL star. And again, this model was a classification model. So these are the inputs that we use, and this is output. And for all of these variables, we converted them into classes. So for example, the PSL star, we converted it into 3 classes. Class 1 between with PSL between 10 and 12, and so on. So in our model, we used 80% of the data for validation and 20% for the final testing. So this algorithm embarrasses a set of hyperparameters that need to be optimized before the training phase. These parameters are the maximum tree depths, the number of trees, T, and the learning rate, L. So in order to optimize these parameters, we need to, we conducted two techniques. The first one is the grid search, and the second one is a 5-fold cross-validation. So I will first go over the grid search. So the grid search, it's an exhaustive research through all possible combinations of values of T, D, and L within a defined space to identify the optimal combination. So in our study, we considered these were the T values that we considered, and these were the D values, and these were the L values. And then the grid search was guided by a 5-fold cross-validation. So in the 5-fold cross-validation, 80% of the training data was divided into 5 subsets, as you can see in this figure. And then the model training was performed using 4 subsets, and the validation was conducted using the remaining subsets. So as you can see that every time we divide our validation data into 5 groups or 5 subsets, and every time the 4 of the subsets are used for the for training the model, and the remaining one is used for validation, and then this this group of data is changed every time. And for every case, we calculate the accuracy, and then we have the average accuracy, which shows us or evaluates the performance of the training for the machine learning model. So for our model, the optimal combination parameters that we got were T of 10, D of 2, and L of 0.5. And the corresponding validation accuracy was 0.73, which is about 73%. So now I will go over the testing for this model. So this shows a confusion matrix using the testing data. So this is the actual PSL star, and this is the predicted PSL star. So let's say, for example, this section, this number showed that when the actual pavement service life of the overlay was class 1, it was predicted correctly 11 times as class 1, and 2 times it was predicted as class 2 and class 3, and so on. So this is a quick explanation of the confusion matrix. So we calculated the accuracy, sensitivity, and specificity of the confusion matrix. And the results generally show that our model is acceptable. A feature in the XGB model is showing the relative importance of the different variables. So this figure shows the relative importance of the different variables that contribute to the output. So as expected, the random cracking index before the application of the overlay had the highest importance. And again, this was expected because we found that the main distress affecting or leading to the failure of the asphalt overlay was the random cracking. So finally, I will just show in this example how state agencies could use this model with an example. So the example is highlighted in red. So first, the AASHTO 1993 design procedure would be used to determine the required thickness. And again, the design PSL would be used as the assumed value of 20. So the required thickness calculated by this procedure, let's say it's 2 inch. So the class for this will be level 1, as we discussed before. And then the state agency will determine the pre-treatment project condition. It will determine the ADT, the age of the pavement, the PCI, RCI, roughness index, and rutting. And again, all of these variables could be easily obtained from the PMS. And then all of these variables will be converted to classes like heavy, old, poor, gold, fair, poor. Again, this is based on the classifications that we provided for the model. And after that, the user will give all of these inputs to the model, and it will and the model will provide PSL star class. So let's say that the PSL star, the output was class 1. So if it's class 3, so if you recall class 3, it's greater than 16. So if the output it's class 3, so we say, okay, this means that this thickness is enough. So we say, okay, so the T final, it's equal to the T initial. So there is no need to adjust the thickness. But if the pavement surface life, if the class is not equal to class 3, so you got like class 1, this means that you will need to raise class 1 to class 2, which means that you need to increase your design overlay thickness. And then with class 2 for the thickness, and again with these project conditions, you will conduct another run, and you will determine the class for the pavement service life. And you will keep repeating this process till the class for the PSL reach class 3. And when it reaches 3, then this will be your design asphalt overlay thickness. So the final conclusion is that the overlay thickness designed with a 1993 design procedure using a PSL of 20 years may not last the entire design period without additional treatment activities. A methodology was proposed to adjust the design overlay thickness such that the resulting actual PSL matches the design PSL. This approach may be used by transportation agencies in the planning phase of future maintenance and rehabilitation activities and in the design phase of structural overlays. So with that, I conclude my presentation, and thank you very much.
All right, great. Thank you. Thank you for agreeing to do back-to-back presentations. So I appreciate that. I am going to move along, but I do encourage you to get a hold of Dr. Musa if you have any questions, or to look at his papers that that will be published for this conference. We do have someone here for our 4th paper, so I want to make sure we give them enough time. This session is scheduled to end at 10:30, and we need to end it at 10:30 or before, because there is another session that starts immediately after this one. So I want to give people time to move from one